Okay, lab 3. So the purpose of this lab is to predict the behavior of circuits containing series and resistors in series and parallel. Use multimeters to measure the actual values of conventional current and potential differences in the circuits and examine the behaviors of ohmic resistors and capacitors. The fundamental principles of this lab is to observe the way that different aspects of resistors and capacitors and how these differences and their setups influence Ohm's law. And the results for this lab is that we had an RC of 6.49 experimentally, but theoretically the RC should have been 6. And then the system is the wire and the whole circuit, and then the surrounding is the rest of the world. So these are the relevant models that are included: Ohm's law, the loop rule, the node rule, potential difference of a capacitor, and the lab-specific formula for calculating an RC. So in part 2 of the experiment, set up a circuit and took ammeter and voltmeter readings at different points on the circuit. So the ammeter read 0.02 when inserted forwards and backwards, and then the voltmeter read that there was a 3-volt potential difference in the system when it replaced the ammeter, and the ammeter read 0, indicating there was no flow of current through the voltmeter that went through the wire, like when the voltmeter was placed into the system instead of the second ammeter. And then when the circuit closes, there was a potential difference of 0 on the wire, negative 0.96 volts for the first resistor, and negative 2.04 volts for the second, adding to negative 3 volts across both. There was a difference of 3 volts in the batteries, so the sum of the potential differences across the whole system was expected to be 0, and it actually was 0, because if you add the 3 volts from the batteries and the negative 3 volts from the resistor, you get 0. So this is the graph of potential versus time across the resistor, and this makes sense. It goes up with the 2 batteries, stays stagnant, and then the first resistor, and then the second resistor, and then it goes back to 0. So our experimental questions: why doesn't the voltmeter affect the ammeter? The voltmeter has a very high resistance, so little current even ends up flowing through it to affect the overall current in the system that the ammeter reads. When the ammeter is in parallel with the 100 ohm resistor, both ammeters read 0.06 because parallel currents affect the flow differently rather than in series. These are just some of the values that I got for part 2. Okay, and then the RC circuit, what happens when to the light when it's connected? Starts off very bright, then fades. Connects in series, the same thing happens. And then what happens to the current? It starts off very large and then falls off. And this is the time it takes to discharge for each scenario. And this is the graphical analysis of the potential difference versus time for the light bulb / capacitor. It starts up very high and then exponentially decreases. Well, this is an exponential, I forget what it is. And then you take the natural log of it using one of the equations from the first side for like an RC circuit, and you get a linear line between the natural log of the potential difference over the initial voltage and time. And then the slope is negative 1.45, and then the RC is equal to 6.49, but the predicted one should be 6 ohms instead of 6.49 ohms, meaning that there was possibly some error. So the error that I thought was that the timing was not automated, so the data results were probably slightly off from when I would hit pause on my timer and then on the program. And then I don't know what predictions the website made for this simulation, but that could have also affected it. So my what if questions: what if you're doing this in real life and use an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter, and how would it have affected the circuits you hooked up? An ideal ammeter has 0 resistance, but a real life ammeter might have resistance, or like some resistance, which decreases the amount of current flowing through it, meaning you would get like a lower value from a voltmeter if you were to test the circuit. And then what if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistance in the circuit? How quickly would our ideal model predict the capacitor in full charge? Would this prediction happen in real life? So, our model would reveal that the capacitor would be charged instantaneously because there's no resistance in the circuit. So, all of that charge would just go into the capacitor. But in real life, there's always some resistance. So, it would be charged quickly but not instantaneously. And yeah, that is the end.